What's up guys, this is Andrew, your computer science teacher for today, and in this video, as we've said, we will implement the fast modular exponentiation, but this time the recursive way. So let's have our project fast modular expo, and this time the recursive manner, right? Finish and go to sources main.cpp, and what we will do here is, as always, we will erase the hello world and we will build our function. And this time our function is going to return an integer, is going to be still called fastexpo, and the parameters are the same, the integer a long which is the n, and our prime modulo number int mod. Now this time, what is a recursive function? It's basically a function that calls itself inside itself. So this function is going to return me, fastexpo is going to return me the result of a at power n, right? So we want to compute this expression modulo mod. If I am in this function, the recursive implementation is way smoother and easier than the iterative one. As we've said, recursive implementations are usually very clear, simple, safer, but with that main disadvantage of the stack memory. So here, basically, I will have two cases. Again, if n is even or n is odd. So if my n is even, n modulo 2 is equal to 0, let's think. If n is even, what is the value of a at power n? Is going to be the value of a squared, all of this at the power n divided by 2. Obviously, this works only if n is even, because if n is odd, this one, it's not an integer anymore. So, for fastexpo of a, n, and mod, its result is going to be actually equal to the result of fastexpo. So I will return fastexpo of a squared. So I need here to have 1ll crossed a modulo mod, all right? Remember that a squared still has to be computed modulo mod because it can get quite big, and with the trick with the 1ll, and n becomes n divided by 2, so here I will have n divided by 2, and I will have mod, right? So as we've said, a at power n is a squared at power n divided by 2. So fastexpo of a, n, and mod is returning fastexpo of a squared n divided by 2 and mod. Now, here, I can write an else, but notice that this else keyword is useless, because if this if statement is satisfied, we will return fastexpo anyway. So this step, this point at this else is not going to be reached anyway, right? So in this case, the else shouldn't explicitly be written because it logically is there. So if n is now odd, what does it mean? What is the value of a at power n when n is odd? Obviously, it's going to be a crossed a at power n minus 1, because this time we can perform the trick with n divided by 2. So I shall return here fastexpo of a n minus 1 modulo, and after I compute a at power n minus 1, so this value, I shall make the product of a and a at power n minus 1. Again with my 1ll trick and everything modulo mod, right? And this is it, guys. This is the function fastexpo. But notice that in the case of recursive functions, we should have a stopping point. We will see more of this in the recursive functions chapter, but right now we can notice that if we don't have a stopping point, this n at each step is either going to be decremented or divided by 2. So let's say if we get here and n is equal to 1 actually, I will have here or here n equals to 0. And if I have here n equals to 0, I call the function again for some n equals to 0. Here I'll have again 0, or I'll have here minus 1. But obviously 0 is even, so I will have here the function call with the new n being equal to 0. So I will have here an infinite loop. I call the function for n equals 0, then I call the function again here for n equals 0, then I call it again here for n equals 0, and so on, which is not great. So the stopping point is when n equals 0, and a at power 0, no matter the value of a, is going to be always returning 1. And that's it, guys. This is the fastExpo function in the recursive manner. Now let's try it out. Let's try again fastExpo of 2 at power 10 modulo that big prime number. All right, 1024, which is pretty great. Let's now try another one, 5 at power 13, let's say. I don't know. Which is going to return me that number. Let's check it with our calculator. So 5 at power 13, right? Which is going to be this number. But when we take this number and we modulo with 1, all right, no, one more 0, no, one more 0 in this one, yeah, we will have this value, right? And I think it matches with our desired result. Again, the corner case here is the power 0, which is very great because we have here the stopping point, so we return 1. So this is the recursive function. As you see, is shorter, is cleaner, but remember, the stack memory hurts a little bit with this one. I really hope that you understood it and enjoyed it, guys, and I can't wait to see you on the next lesson. Bye bye.